Welcome to Orbit Observer. Settle in wherever you are, let your shoulders come down from your ears, let the weight of the day go soft, and let your breathing find its own slow rhythm. Because tonight we are not going anywhere in a hurry. Tonight we drift. And the place we're drifting toward is very far away, and very old, and very quiet. And I promise you it asks nothing of you except that you rest while I keep watch. Let me begin with a single object, moving through the dark. In the summer of 2025, something crossed the far side of our solar system that had no business being here. It came in fast, and I mean fast in a way that is hard to hold in the mind, so let me give it to you gently. It was travelling at roughly 58 kilometres every second. Not every hour, every second. In the time it takes you to draw one slow breath in and let one slow breath out, this thing had already covered more distance than the entire width of a small country. It came steaming past the orbit of Mars, out beyond us, on the opposite side of the Sun from where the Earth happened to be sitting. And it never slowed, and it never turned, and it will never come back. And here is the strange part, the part I want you to carry with you as you fall asleep. Because it is the kind of fact that sounds like a made-up thing, and yet, as best as anyone can tell, is very likely true. This object was probably older than the Sun. Older than the Sun. Take a moment with that. Our Sun is about 4.5 billion years old, and everything you have ever known, every ocean and every mountain and every living thing that has ever drawn breath, formed after the Sun did, in the leftover material that circled it. The Sun is the elder of everything in your world, and yet the best models we have suggest that this cold, dark visitor, this fragment steaming quietly past Mars, may have been drifting through the galaxy for more than 7 billion years, which means that when the cloud of gas and dust that would one day become our Sun had not yet even begun to collapse, this thing was already old. It had already been wandering, in the black, between the stars, for longer than our entire solar system has existed. It was given a name that is almost a code. 3I Atlas. And in a little while I will tell you exactly what each part of that name means, and how anyone could possibly claim to know the age of a rock that no one has ever touched. But not yet. For now I only want you to feel the shape of it, that something impossibly ancient came gliding through our neighbourhood in 2025, showed itself for a few months, and then slipped back out into the dark forever. And it was not the first. That is the thing I want to hand you tonight, the quiet revelation we are going to walk toward together, slowly in the dark, at the pace of someone with nowhere else to be. Because 3I Atlas was not a freak. It was not a one-off. It was the third. 3 times now, in a window of just 8 years, a visitor from another star has crossed through our solar system. 3 confirmed travellers, each one born around a different sun, each one flung out of its home long ago and left to drift, and each one passing through our little pocket of space, just close enough, just briefly enough for us to catch it. And here is the part that turns a set of headlines into a genuine mystery, the thread I want us to follow. Each of these 3 visitors broke a different rule. Each one arrived and quietly demolished something that astronomers had assumed was simply true. Not the same surprise 3 times over, 3 different surprises, stacked on top of one another, and when you lay them side by side, they point at a single conclusion that is both enormous and strangely peaceful. That conclusion, the thing we are drifting toward, is this. The space between the stars is not empty. We were taught, all of us, in some quiet way, to picture the gulf between the stars as a vast and perfect nothing, a black ocean with the stars as distant, lonely lighthouses, and nothing at all in between. And that picture, it turns out, is an illusion. The dark between the stars is not empty. It is filled. It is thick with the cast-off debris of billions of other solar systems, with fragments and shards and frozen splinters of worlds that formed and broke and scattered long before we were here to wonder about them. The galaxy is quietly saturated with these drifting things. They have been streaming past us the whole time. The only thing that changed, the only thing, is that in the last few years we finally built eyes fast enough and wide enough to see them go by. So that is our journey tonight. 3 visitors. 3 broken rules. 1 quiet truth about the sky. And I am going to take you through all of it slowly, one at a time, from the very first, so that you can drift off at any point along the way and lose nothing, because the wonder of this is not in racing to the end. The wonder is in the descent. Before we go down, one small thing, and then I will not interrupt the dark again. If you find, somewhere in the middle of this, that you have quietly fallen asleep, good. That is the whole idea, and if you are still with me, I would love to know where in the world you are listening from tonight. Whatever city, whatever quiet room, whatever hour it is where you are. Leave it in the comments if you feel like it. I read them, and it is a lovely thing to imagine all of you scattered across the planet, drifting off under the same old sky. And if you are new here and you'd like more slow journeys like this one, you can subscribe and I'll keep making them. Now, let the room go quiet. Let the light go low. And let's go back to the beginning of the story, back to the first of the 3, back to a mountaintop in Hawaii on an autumn night in 2017. It began, as these things so often do, with a telescope simply doing its patient, unglamorous work. High on the slopes of Haleakalā, on the island of Maui, there sits an observatory. Haleakalā is a volcano, and its summit rises far above the clouds into some of the clearest, stillest air on Earth, which is exactly why we put telescopes up there, in the thin, cold dark, where the stars do not twinkle so much as simply burn. And on that mountain there is an instrument called Pan-STARRS-1, which is a wonderful, workmanlike sort of machine. Its job is not to stare at any one beautiful thing. Its job is to sweep. Night after night, it photographs great swaths of the sky, again and again, and then patient software compares each new image to the last, hunting for anything that has moved, anything that is new, anything that was not there the night before. Most of what it finds is ordinary: asteroids tumbling along their familiar loops, comets on their long, slow returns, the known traffic of the solar system catalogued and expected. On the night of the 19th of October 2017, an astronomer named Robert Weryk was looking through that stream of images, and he found something that did not fit. There was a faint smudge of light, moving, nothing dramatic. Not a fireball, not a flash, just a dim little point creeping across the star field from one night to the next. But when he tried to fit its motion to an orbit, when he tried to draw the curved path it must be following around the sun, the numbers refused to cooperate. He could not make it into a normal solar system object, no matter how he tried. And slowly, as more measurements came in and the calculation sharpened, the truth of what he was looking at became clear, and it was a truth no human being had ever confirmed before. This thing was not from here. It was not bound to our sun at all. It was not one of ours. It had come in from the outside, from the dark between the stars, dived down toward the sun, whipped around, and was already on its way back out, never to return. It was the first object from another star system that we had ever caught passing through our own. The first confirmed interstellar visitor in all of history. They gave it a name, and the name is beautiful, and it comes from the Hawaiian language, in honor of the mountain and the islands where it was found. Oumuamua. It means, roughly, a scout, or a messenger reaching out to us from the distant past. A thing sent ahead. And that is exactly what it was, a messenger from somewhere else, carrying, in its very existence, a message we were only beginning to be able to read. And because it was the first of an entirely new kind of thing, astronomers had to invent a whole new category to hold it. Every comet and asteroid we track carries a designation, a little cataloguing name. But there had never been a class for objects that come from beyond the Sun's family, because until that October night, we had never confirmed one existed, so they made a new one. They called the class I, simply I, for interstellar, and Oumuamua, being the first, became 1I, the one that opened the door. Every visitor that has come since is measured against it, numbered after it. 1I Oumuamua, the first of its kind and the beginning of everything we're going to talk about tonight. Now, I told you that each of these three visitors broke a rule, and I want to be honest and precise about what that means, because the honest version is more astonishing than any exaggeration. So let me first show you how we knew, beyond any doubt, that Oumuamua was truly from somewhere else. Because that alone, before any of the deeper strangeness, was already a quiet earthquake. The key to it is a single number, and the number describes the shape of a path. When an object moves through the solar system, the Sun's gravity bends its path into a curve. If the object belongs to the Sun, if it is one of the family, a planet or an asteroid or a comet that circles back again and again, that curve closes on itself. It's a loop. The object comes in, swings around, and heads back out along a path that will eventually bring it home again. Everything the Sun owns travels on a closed loop like that. That is what it means to belong to a star. But there is another kind of path. If an object is moving too fast, if it has too much speed for the Sun's gravity to ever rein it in and pull it back, then the curve does not close. It opens, the object comes swinging in, bends around the Sun once, and then flies off along a path that never returns, a path that carries it away from the Sun forever. Astronomers have a word for that open, one-way, never-returning shape. They call it a hyperbolic orbit. And a hyperbolic orbit is the unmistakable signature of something that does not belong to the Sun. Something that was only ever passing through. There is a way of putting a number on this, on how open or how closed a path is, and it is called the eccentricity. And I want to give you this number gently, because it is one of the quiet heroes of the whole story. Think of eccentricity as a measure of how stretched a path is. A perfect circle has an eccentricity of 0. A normal, comfortable, closed orbit, the kind of loop that belongs to the Sun and comes back around, has an eccentricity somewhere below 1. That number 1 is the great dividing line. Below 1 you are bound, you belong, you will return. Above 1 you are free, you are unbound, you are only visiting, and you will never come back. Oumuamua's eccentricity came out at about 1.2, above 1. Comfortably, unambiguously above the line. Not a borderline case, not a maybe, not a rounding error, 1.2. Clearly on the far side of the boundary, in the territory that can only mean one thing. This object was never captured by the Sun. It was never ours. It came in from outside on a one-way path, and it left on a one-way path. and the number that proved it was as clean and simple as that. 1.2. A little over the edge. A visitor. And you could see it, too, in how fast it was moving when it was still far from the sun, out where the sun's pull is weak, and an object more or less coasts along at whatever speed it truly carries. That baseline speed, the speed a thing has out in the deep before the sun starts tugging on it, astronomers call the V infinity, the velocity it holds out at, effectively, infinity, far from everything. It's a way of asking, stripped of the sun's influence, how fast is this thing really going through the galaxy? For Oumuamua, that answer was about 26 kilometers every second. 26 kilometers a second, just as its natural, resting, cruising pace through interstellar space, the speed it had been carrying for who knows how long before it ever found us. That is not a speed the sun could give something and then take back. That is the speed of something that was already moving, on its own, through the dark, long before it arrived. So it fell inward, faster and faster, as the sun's gravity took hold and pulled, the way anything falls faster the closer it comes. And it came remarkably close. On the 9th of September 2017, and here is a small strange thing, that this was more than a month before anyone on Earth had even noticed it existed, Oumuamua reached the closest point of its swing around the sun. That closest point has a name too. It's called perihelion, which simply means the nearest approach to the sun, the bottom of the dive. The moment of greatest speed and greatest heat before the object begins to climb away again. And Oumuamua's perihelion brought it in to about a quarter of the distance between the Earth and the Sun. 0.255 in the units astronomers use, closer to the Sun than the planet Mercury ever gets. It dove down inside the orbit of Mercury, into that fierce, bright inner region where the sunlight is blinding and the heat is enormous, whipped around the far side and started back out. And that timing matters, because it is a little heartbreak folded into the story. By the time Robert Weryk found that faint smudge on the 19th of October, Oumuamua had already rounded the sun weeks earlier. It was already leaving, already outbound, already climbing back toward the dark it had come from, already beginning to fade. We did not catch it arriving. We caught it in the act of departing, over our shoulder as it walked away. Everything we would ever learn about the first interstellar object humanity ever confirmed, we learned in a hurry, in the narrow closing window of a farewell, watching a stranger's back as it receded into the night and knowing the entire time that we would never ever see it again. Think about that, softly, as you lie there, somewhere out beyond the planets, right now, in the black, Oumuamua is still going, still climbing away from the sun, slower now, but never stopping, carried by that unbound path, that eccentricity a little over 1. Out and out and out, back toward the stars. It has been travelling away from us for years, and it will travel away for millions more, and no eye and no instrument will ever fall upon it again. It gave us a few short weeks, and then it was gone. For most objects, that would be the end of a small, tidy story. A rock came from far away, we glimpsed it, it left. Remarkable, but simple, a first, and then a full stop. But Oumuamua would not let us have it simple. Because in those few short weeks that we watched it, in that hurried glimpse over the shoulder, it did something that no one could explain. It behaved in a way that a bare, dead rock should not be able to behave. It broke the first of our 3 rules, and it broke it so cleanly and so mysteriously that people are still arguing about it to this day. And that is exactly where we are going next, down into the strangeness of Oumuamua itself, into the shape of it and the colour of it, and the impossible little thing it did on its way out the door. But let me hold you here for just a moment longer, on the edge of it, because I don't want to rush you over the threshold. I want you to feel where we are in the story before we go deeper. We have, so far, just one object. The first, discovered by patient machinery and a watchful astronomer on a volcano in Hawaii on an October night in 2017. We have proven with a single clean number that it truly came from beyond the Sun. We have watched it dive inside the orbit of Mercury and turn and start to leave, and we have understood, at least in outline, the enormous fact that its mere existence hands us that there are things out there in the dark between the stars that can come this way, that the door, which we always assumed was shut, is not shut at all. Objects can cross from one star's realm into another's. Ours is not sealed. Ours is not private. The traffic exists. And already, before we even get to why Oumuamua was so strange, this quietly changes the shape of the sky above you. Because if it is possible at all, if a thing can drift out of one star system and into another, then the only real questions left are how often, and how many, and whether we simply hadn't been watching carefully enough to notice. We'll come to those questions. They have answers now, or at least the beginnings of answers, and the answers are staggering. But they wait for the end of our journey, for the moment when we lay all three visitors side by side and finally understand what having three of them really means. For now, drift with just the one, the scout, the messenger reaching out from the distant past. One-eye Oumuamua, faint and reddish and tumbling, already leaving before we ever knew it was there, carrying in its odd little body a mystery that would divide the people who study the sky. Let your breathing slow. Let the number settle in your mind, and then let it go. 1.2. The little proof. The mark of a visitor. You don't need to hold on to anything. I'll carry the facts for you. That's what I'm here for. All you have to do is rest and let the story move around you like water, while somewhere far above this quiet room the real sky turns, and the real dark stretches out between the stars, fuller than we ever imagined, holding its slow and drifting cargo. And here is the thing I want you to know as we prepare to go deeper. When Oumuamua was found, astronomers had a very tidy way of sorting the small bodies of space into two neat boxes. On one side, comets, the icy ones, the ones that come in from the cold and, as they near the sun and warm, begin to steam, releasing gas and dust into a great glowing halo and a long streaming tail, that soft bright fuzz we all recognize as the classic picture of a comet. And on the other side, asteroids, the dry ones, the bare rock and metal, dead and dark, no ice to steam, no tail, no halo, just a hard little body reflecting sunlight and nothing more. Comet or asteroid, icy or rocky, steaming or bare. For generations, everything we found fit, more or less, into one box or the other. It was one of those quiet assumptions that felt less like a theory and more like simple common sense. A small body in space is either a comet or an asteroid. What else could it possibly be? Oumuamua looked, in every visible way, like an asteroid. A bare rock, dead and dry. No halo of gas around it, no glowing coma, no streaming tail. Nothing at all to suggest ice quietly boiling away in the sunlight. We watched it closely in those hurried weeks with the best instruments we could turn toward it, and we saw no dust, no gas, no comet-like activity whatsoever. By every appearance, it was firmly in the asteroid box, a cold, dead, tumbling stone. And then, on its way out, that cold, dead tumbling stone put its foot on the accelerator. But that, the impossible little shove, the thing that should not have happened, the moment the tidy two-box world quietly fell apart, that is where we'll begin when we go deeper. Because to understand why it stunned the people who saw it, you first have to understand exactly what Oumuamua looked like, and how it moved, and just how bare and engineless a thing it truly appeared to be. And I'll walk you through all of it slowly, the brightness that swung wildly as it turned, the strange stretched shape that no one could quite agree on, the reddish weathered surface, all the pieces that made the little shove at the end so utterly impossible to explain. So stay soft, stay slow. There is no hurry at all. We have 2 more visitors waiting after this one, each stranger than the last, each breaking its own rule, and a truth about the whole sky waiting at the end of the road. But the road is long and gentle, and we are going to take every step of it in our own good time, in the dark, together, while the real objects drift on unseen far above, and the space between the stars goes on, quietly filling in. Let's stay with Oumuamua a while longer. Let's look at what it actually was. It begins, as so many of these stories do, with someone at a screen in the middle of the night looking at pictures of the sky that a machine had taken while most of the island slept. The 19th of October 2017, the place was Haleakalā, the great shield volcano on the island of Maui, and near its summit sits a telescope with a strange and fitting name, Pan-STARRS 1. The first of the Panoramic Survey Telescope and Rapid Response System. Its whole purpose is patience. Night after night, it sweeps the same wide fields of stars, taking image after image, and then it compares them, looking for the one point of light that has moved since last time, the one thing that does not belong. The man who found it was Robert Weryk. And what he saw at first was simply a faint smudge that had shifted against the fixed stars, the kind of moving dot that usually turns out to be a near-Earth asteroid, one more piece of local rubble on a familiar loop around the sun. Nothing about that first glimpse announced itself. There was no flash, no signal, no sense in the moment that anything had changed, just a dim little traveller caught in the act of crossing the frame. But the numbers would not settle. As more observations came in and the path of the object was traced back and forth across the sky, the shape of its orbit refused to close. That is the quiet, technical heart of this whole story, so let me lay it out gently, because everything else grows from it. Nearly every object we had ever tracked in the sky belonged to the sun. It rode an ellipse, a stretched circle, a closed loop, and no matter how long or lazy that loop might be, it always came back around. The measure of how stretched a loop is, astronomers call the eccentricity. A perfect circle has an eccentricity of 0. A long, drawn-out cometary ellipse creeps closer and closer to 1. But 1 is the wall. 1 is the edge of belonging. Cross past it, and the path is no longer a loop at all. It becomes a hyperbola, an open curve that sweeps in once, bends around the sun, and flies back out forever, never to return. And this little smudge from Haleakalā had an eccentricity of about 1.2. Not 1.01, where you might argue and squint and blame the measurement. 1.2. Comfortably, unmistakably, impossibly past the wall. This thing had not come from around the sun. It had never been bound to the sun at all. It had come in from the outside, from the black country between the stars, moving too fast for the sun to ever hold it, and it was already on its way back out into that same dark before we even knew it was here. They gave it a name from the language of the island where it was found. Oumuamua, a Hawaiian word that carries the sense of a scout, a messenger reaching out from the distant past. The first of something arriving ahead of the rest. And then they gave it a designation, a piece of formal bookkeeping that was, in its own dry way, one of the most extraordinary things about the whole encounter. They called it One Eye. The number 1, because it was the first. And the letter I for a brand new category of object that had never before needed to exist. Interstellar, until that October, humanity had comets and we had asteroids, and every single one we had ever catalogued belonged to our own sun's family. Now, for the first time, we needed a box for things from somewhere else entirely. And Oumuamua was the reason the box was built. Object number 1 in a class of its own. Think, for a moment, about how fast it was truly moving, because the orbit alone doesn't quite convey it. Far from the sun, out in the deep where the sun's pull barely reaches, this object was already carrying a speed of its own, what the astronomers call its velocity at infinity, the pace it held before our star ever got a grip on it. About 26 kilometers every second. That is the speed it was born with, out there among whatever stars it came from, the leftover motion of its long crossing. The sun did not give it that speed. The sun only bent its path a little as it passed, the way a stone in a river bends the water around it without ever stopping the flow. And it did pass close, closer than you might imagine for something we barely caught. Its nearest approach to the sun, its perihelion, had come on the 9th of September 2017, more than a month before Weryk ever saw it. At that closest point it swung in to about a quarter of the distance between the Earth and the Sun. 0.255 of an astronomical unit, to put a number on it. That is well inside the orbit of Mercury, inside the innermost planet, into the fierce bright heat close to the star, where any ordinary comet would have been screaming with released gas and glowing dust. Oumuamua rounded that fire, took the sun's gravity like a slingshot, and came whipping back outward, and only then, on its way out, and already climbing away from us, did our telescopes finally happen to catch it. So understand what that means for the story. By the time anyone on Earth knew this visitor existed, it was already leaving. We had missed its arrival entirely. We had missed its closest, brightest, most revealing moment. What we had was the tail end of a single crossing, a few precious weeks of a faint and fading dot, moving away faster every night, never to be seen again by anyone, ever. There would be no second look. No return in a decade or a century. No chance to send anything after it in time. One pass, one handful of nights. And then gone, back into the dark it came from, carrying whatever answers it held away with it at 26 kilometers a second. And in those hurried weeks, with the clock already running out, the astronomers pointed everything they could at the departing smudge and tried to learn what it was. What they found only deepened the strangeness. The first thing to understand is that most of what we can know about a distant object in space comes from its light. Not from touching it, not from orbiting it or landing on it, not from any instrument placed close enough to taste its surface chemistry directly. Light. The object reflects some fraction of the sunlight that falls on it, and that light travels across hundreds of millions of kilometers and falls into the aperture of a telescope, and the telescope records it. And from those faint arriving photons, the astronomers must do the difficult, patient work of reconstruction, of inferring a shape, a surface, a rotation, an identity, the way a detective pieces together a story from a handful of traces left behind at a scene that nobody witnessed. With Oumuamua, the light told a story that took a while to believe. As the observatories tracked it in those October and November nights of 2017, they watched its brightness change. This is not unusual. Almost everything in the solar system rotates, and when an irregular body rotates, the amount of surface it presents to the sun changes, and so the amount of sunlight it reflects changes. And the telescope records that oscillation as a brightening and then a dimming that repeats on some steady cycle, like a lighthouse turning. From the speed of that cycle you can infer the rotation period. From the amplitude of the swing, how much brighter and how much dimmer it gets, you can begin to infer the shape. A nearly spherical object, like a ball, barely changes brightness as it spins, because it always presents roughly the same cross-section. An elongated object, something more like a log or a plank, brightens dramatically when its long face swings toward you and fades just as dramatically when its narrow end points your way. Oumuamua's brightness swung by a factor of roughly 10. That is an extraordinary number. One end of its brightness range was 10 times brighter than the other. Set that against what is typical for solar system asteroids and comets, where a factor of 2 or 3 is already considered elongated, where a factor of 5 marks something genuinely unusual, and the factor of 10 sits at a level that most scientists, if you had suggested it beforehand, would have described as essentially impossible for a naturally tumbling rock. A factor of 10 implies an object so stretched in one direction compared to another that the two dimensions are barely on speaking terms with each other. The rotation period worked out to somewhere in the range of 7 to 8 hours. And crucially, the tumble was not clean. It was not the steady, graceful spin of a top. It was a chaotic, end-over-end wobble, the kind of rotation that happens to an object that has been struck or stressed or torn and left spinning irregularly across a long and eventless passage through space. As if something had happened to it, long ago, in some other place, and it had been tumbling ever since in whatever posture the violence left it. From the brightness swing and the tumble period, the astronomers began to calculate what shape could produce such numbers. The earliest models converged on something elongated well beyond anything in the solar system's catalogue, an axis ratio of at least 5 to 1, possibly 6 to 1. Some analyses pushed toward 10 to 1. The long axis somewhere between 100 and 400 meters, a size that makes it roughly as long as a skyscraper is tall at the generous end, or about as long as a city block at the conservative end. Not large by the standards of space. A modest fragment of something, but shaped in a way that no asteroid or comet nucleus in the solar system had ever been found to be shaped. The early images in the popular press reached for the word cigar, a tumbling cigar of alien origin, which had a satisfying strangeness to it and was not entirely wrong as a first approximation. But as the data analysis deepened, some researchers began arguing for a different shape. Not a cigar, but something flatter, a disc, perhaps, or a pancake, or a thin wafer, spinning and tumbling so that it caught the sunlight differently depending on which face was turned toward the telescope. The disk model had its own adherents and its own arguments, and the honest answer, which is the only honest answer available, is that the true three-dimensional shape of Oumuamua cannot be known with certainty from the data that exists. What is certain is the extreme brightness swing, and what that swing requires, an object whose proportions depart from the ordinary far enough to rank as the most elongated natural body ever observed, whatever its exact shape. Oumuamua was something that nothing in the known catalogue had prepared the solar system's cataloguers to expect. Its colour, such as it could be measured in those brief weeks, was reddish. Not dramatically so, not unlike some objects in the outer reaches of the solar system, certain Kuiper belt bodies carry that same muted red-brown tint, believed to arise from organic material on the surface that has been cooked and darkened by billions of years of cosmic radiation. It is what happens to the chemistry of a surface when it sits unshielded in the deep between star void long enough, absorbing the slow and relentless irradiation of the galaxy. The colour was not alien in a startling sense. It was, if anything, the colour of ancient processed material, an outer crust tanned and altered by time and radiation into something durable and dark. And then there was the question of the tail, or rather, the absence of it. When a comet enters the inner solar system, when it crosses inside roughly the orbit of Mars and the sunlight begins to warm its surface with real intensity, what happens is a process that astronomers call outgassing. The comet's nucleus is not solid rock throughout. It is more like a dirty snowball, or perhaps more accurately a mixture of ices and dust and organic material loosely bound together. And when sufficient heat reaches the surface, those ices sublimate directly from solid to gas without passing through a liquid stage. Water ice, carbon dioxide, carbon monoxide, various volatile compounds, they lift off the surface as gases, carrying dust with them, expanding into a cloud around the nucleus called a coma. And then the pressure of sunlight and the stream of charged particles from the sun push that cloud into the trailing tail that we see stretched across the night sky behind a bright comet. The coma and the tail are the calling cards of a comet. They are how you know it is a comet. They are, in a deep sense, what makes a comet a comet. Oumuamua passed through the inner solar system to within a quarter of the Earth-Sun distance, deep inside the orbit of Mercury, where the sunlight is fierce and concentrated. Any ordinary comet nucleus of the size estimated for Oumuamua would have been producing a visible coma. It would have been showing gas. It would have been leaving a dust trail. These are not subtle effects, they are precisely what telescopes are designed to detect. The astronomers looked. They looked carefully, and they kept looking. Through the weeks the object was observable. And they found nothing. No coma, no gas, no dust, no tail of any kind. Oumuamua looked, in every observable respect, like a bare rock. A bare, extreme, tumbling, reddish, cigar or pancake-shaped rock, passing through the warmest, most revealing part of our solar system, and showing none of the volatiles that every comet shows. This, too, was a violation of expectation. Interstellar space is cold beyond description. The temperature in the void between stars is just a few degrees above absolute zero. Cold enough to preserve ices indefinitely over billions of years, and an object arriving from interstellar space might reasonably be expected to carry deep reserves of frozen volatile material. Oumuamua either had no such reserves or had lost them during an earlier close pass to some other star, or had somehow developed a surface crust so thick and inert that any remaining ices were sealed beneath it, unable to sublimate. None of these explanations was entirely satisfying. All of them required a set of assumptions about an object's history that could not be verified from the available data. And so, by December of 2017, as Oumuamua climbed away from the sun and faded toward the limit of detection, the picture looked like this. An interstellar visitor, unmistakably not from here, with a shape unlike anything in our solar system. With no coma and no tail despite its inner solar system passage rotating chaotically on a long period. Strange, genuinely strange. But not yet physically impossible. Then came the acceleration. This is the part that moved the strangeness from the category of unusual into the category of genuinely unresolved. In 2018, a team of researchers led by Marco Micheli, working with data from multiple observatories, published their analysis in the journal Nature. They had done something that seems simple, but is in practice exquisitely difficult. They had taken all the positional measurements of Oumuamua taken over the weeks it was observable, and they had fit those positions to the trajectory that gravity alone would predict. And they had compared the predicted positions to the actual measured positions. This is the standard method for understanding how a solar system object is moving. The sun's gravity bends and controls the path, and if you understand the starting conditions well enough, the gravity equations should match the observations almost perfectly. They did not match. Oumuamua was in a different position than pure gravity said it should be. Specifically, it was moving faster than gravity alone would carry it. As it climbed away from the sun, it accelerated. Not a large acceleration, the total effect was small, but it was measurable. It was consistent across multiple independent observations, and it was real. Something was pushing Oumuamua away from the sun with a force beyond what gravity alone could produce. In the solar system, when an object accelerates in ways that pure gravity cannot explain, the first and most obvious explanation is what astronomers call non-gravitational forces. For comets, the mechanism is well understood: the outgassing. The jets of sublimated volatile material venting off the nucleus push back against the comet the way a thruster pushes a spacecraft. The force is small but real, and it is directional, and it is measurable, and it shows up in precisely this way, as a deviation from the purely gravitational trajectory. But Oumuamua had no outgassing, none that anyone could see. No coma, no gas, no jets. The telescope that would have detected outgassing at the level required to produce the observed acceleration found nothing. The push was there. The mechanism was not. This is what the Micheli et al. Paper reported. A non-gravitational acceleration, real and statistically unambiguous, with no visible source to account for it. A body that behaved, in its trajectory, like a comet being pushed by its own escaping gas, and yet showed no gas. The comet's engine without the comet's smoke. The scientific community did what it always does with a genuine anomaly. It generated hypotheses. Many of them. Some more plausible than others. The most conservative explanation, and the one that many researchers still consider the most likely, is that Oumuamua was outgassing after all, just doing so in a way that was invisible to the instruments looking for it. If the material being released was something other than dust-laden water vapour, something cleaner and more transparent, a gas that does not produce the usual coma signature, then the push could exist without the visible tell. Carbon dioxide outgasses differently from water. There are conditions under which a body could release enough material to produce a measurable force while leaving almost no dust behind, and therefore leaving almost no detectable coma signature. It is a narrow set of conditions. It requires a specific chemistry and a specific geometry of outgassing. But it is physically possible, and it has the considerable virtue of requiring no new physics. Others reached further. Two research teams working independently, Jackson and Desch at Arizona State University and Seligman and Laughlin in a related line of work, proposed an explanation that is, in its way, genuinely beautiful in how much explanatory work it does with a single assumption. They proposed that Oumuamua might be a fragment of nitrogen ice, a shard chipped off the outer surface of a body, something like Pluto. The large, cold, distant worlds that are thought to exist around other stars, just as they exist in the outer reaches of our own system, covered in thick layers of exotic ices, including nitrogen ice, at temperatures so low that the chemistry becomes deeply unusual by inner solar system standards. Nitrogen ice is essentially transparent. It does not produce the dusty, opaque coma of a water ice comet. It sublimates at very low temperatures, much lower than water ice, and the gas it releases is nitrogen, which is not easy to detect at interstellar distances. And importantly, the mathematics worked out. An object of the right size, made of nitrogen ice, losing mass by sublimation as it passed through the solar system, would lose that mass asymmetrically in a way that would push it, gently and invisibly, in approximately the direction and at approximately the rate that was observed. The same process that drives standard cometary non-gravitational acceleration, but with a material so transparent that the evidence destroys itself in the act of producing the effect. The nitrogen ice hypothesis also offered a natural explanation for the shape. As a nitrogen ice body sublimates, as its outer surface slowly vaporizes away, the ablation is not uniform. The face exposed to sunlight loses material faster than the shadowed face. Over a long transit, this differential erosion would gradually flatten a body, pressing it from a more rounded original shape into something thinner and wider, more like a wafer or a pancake, which would in turn produce something much like the extreme brightness oscillations that Oumuamua displayed. The shape and the acceleration in this model would both be explained by the same mechanism, slow sublimation of an invisible ice. The fractal dust bunny hypothesis arrived from a different direction entirely. Some researchers proposed that Oumuamua might not be a coherent solid object at all in the usual sense, that it might instead be an extremely porous, loosely bound aggregate of fine dust particles, something resembling a very large, very fragile snowflake, or a loosely clumped cloud of interstellar dust grains held together by weak forces with a density far lower than any solid rock. Such an object would have an enormous surface area relative to its mass, and sunlight exerts pressure on all surfaces. This is the well-established phenomenon of radiation pressure, which is real and measurable and is already accounted for in precise orbital calculations for most objects. Normally, the effect is tiny because solid rocks have small surface areas relative to their masses. But a large, extremely porous, extremely low-density aggregate could have surface-to-mass ratios high enough that sunlight pressure alone would produce the observed acceleration without any sublimation at all. A cosmic dust bunny blown gently away from the sun by the pressure of its own light. Each of these hypotheses is physically coherent. Each makes specific predictions about the kind of object Oumuamua would have to be, predictions that cannot be verified because the object is gone, climbing into the dark at 26 kilometers a second, forever beyond the reach of any instrument. And then, at the edges of the scientific community, where the fringe presses against the boundary of the mainstream, a different kind of proposal appeared, It deserves mention because it was published, because one of its authors, Avi Loeb, then chairman of the astronomy department at Harvard, is a serious scientist with a long record of legitimate work, and because the public discussion of Oumuamua cannot honestly be told without acknowledging it. But it deserves to be clearly and precisely labelled for what it is. Loeb and his co-author Shmuel Bieli published a paper in late 2018 proposing that the observed properties of Oumuamua, the extreme shape, the lack of coma, the anomalous acceleration consistent with radiation pressure, were also consistent with the properties of a thin, artificial structure, something like a light sail, which is a technology that has been seriously proposed in the context of human spaceflight, involving large, extremely thin sheets of material that can be pushed across interstellar space by concentrated laser beams or by sunlight alone. If Oumuamua were a sheet of artificial material, thin enough that sunlight could push it meaningfully, it would behave in roughly the ways that were observed. This is a minority hypothesis. It is the position of essentially no one working in mainstream planetary science or cometary dynamics. The competing natural explanations, and there are several of them, each with serious scientific advocates and detailed quantitative modelling behind them, do not require invoking artificial origin. The principle known as Occam's razor, which is simply the scientific habit of preferring simpler explanations that require fewer extraordinary assumptions when multiple explanations are on the table, points strongly away from the artificial hypothesis. The silence of Oumuamua, the absence of any signal, any emission, any structure observable at any wavelength, is consistent with a natural object and is not, by itself, evidence of artificiality. Silence is what both a bare rock and an inactive probe would produce. It is recorded here because it happened, because the papers exist, because it became part of the public conversation around this object in ways that cannot be erased. But it is not the reason Oumuamua matters. The reason Oumuamua matters is simpler, deeper, and considerably more interesting. It was the first object ever confirmed to have come from outside the solar system. It had properties unlike anything catalogued before it, and it left before we could answer the most important question it raised. The anomaly is real. The physics that produced it remain, in the strict and honest sense, unresolved. The parked question: what pushed it? What material made it? What it truly was when it rounded the sun in September of 2017, weeks before any human eye knew it existed, has no settled answer. That question stays open. Not because the scientists stopped working on it, but because the data ran out before the answer could be extracted, and Oumuamua will not be returning to offer a second chance. And so the first rule it broke is this: the dichotomy between a comet and a rock, which had seemed firm enough to build a taxonomy on, could not hold. Oumuamua accelerated like a comet while showing no coma. It defied the comet label and defied the asteroid label simultaneously, and in doing so it forced astronomers to confront the possibility that the categories built from solar system objects might not be universal, that the objects produced by other planetary systems, shaped by other conditions, aged by other histories, might not sort cleanly into the bins that our own system's inventory had established. The first visitor broke the first assumption so cleanly and so completely that even now, years later, the debate about what it was has not reached a conclusion that satisfies everyone. Quick reminder: after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. Oumuamua faded below the detection threshold of every telescope on Earth in January of 2018. The last observations were collected in November and December of 2017, when it was already farther from the Sun than Mars and growing dimmer at every pass. The analysis continued long after the object itself was gone. The papers kept arriving, the debates kept circulating, the hypotheses kept multiplying and being refined, but the object itself was over the horizon, irrecoverable, carrying its unresolved physics back toward whatever dark cloud of stars it had drifted from. The exact direction of its origin is known roughly: the constellation Lyra, the vicinity of the bright star Vega, though the travel time is so long and the trajectory so curved by the Sun's gravity that pinpointing an actual home system is not meaningfully possible with the data available. It came, roughly, from that direction over some vast and uncalculable timescale. And then it passed, and was gone. What it left behind was not an answer. It left behind a question so pointed and so stubborn that it changed the direction of the field. And it left behind something else, something perhaps more important, the knowledge that the category was real, that interstellar objects existed, that they passed through the solar system on trajectories that could be confirmed and measured, that they could be found if the telescopes were looking in the right way, that the galaxy was not keeping its material entirely to itself. For 2 years, Oumuamua was the only example, a sample size of 1. And a sample size of 1 is, in science, essentially impossible to draw conclusions from. A single anomalous object could be anything, a statistical fluctuation, an outlier so extreme it will never be repeated, a once-in-a-lifetime curiosity that belongs in no category because categories require repetition. The astronomers went on thinking and modelling and debating and waiting. The surveys kept sweeping the sky, the nights kept accumulating. And then, on the 30th of August 2019, less than 2 years after Oumuamua disappeared over the horizon, a man sitting in a dome in Crimea looked at an image on a screen and saw something that did not belong there. His name was Gennadiy Borisov. He was not, by the formal definition, a professional astronomer. He was an amateur, a word that carries, in some contexts, a faint suggestion of the informal or the approximate, but which carries here the deeper original meaning, from the Latin for love. Someone who does it for love. Borisov had built his own telescope, a 65-centimeter instrument, roughly the diameter of a large dinner table, which is not small for an amateur's construction, assembled by hand, in Crimea, at an observatory he had built himself. Because the night sky was something he had devoted a large portion of his life to observing with equipment he had made. And on that August night, moving against the fixed background of stars in a way that marked it as something in our solar system, he found a comet. Not an unusual event in itself. Comets are found regularly, and amateur astronomers find their share of them, often because a dedicated amateur with a purpose-built instrument and a clear sky can cover patches of sky that the automated surveys, with their specific scan patterns and scheduling constraints, do not always prioritize at the right moment. But this one, as the follow-up observations accumulated over the days after Borisov's discovery, began to reveal something extraordinary in its orbital numbers. The orbit was hyperbolic. Not slightly, not ambiguously. The eccentricity came in at approximately 3.36, far above the 1.2 that had already seemed remarkable for Oumuamua, far above the value of one that separates everything that belongs to this solar system from everything that does not. 3.36 is a number that leaves no room for interpretation. This object was not bound to the Sun. It was not a long-period comet returning from the Oort cloud after a million-year absence. It was not from here at all. It had arrived from interstellar space, from the orbit of another star, moving at roughly 32 kilometers every second relative to the Sun at infinity, which is the standard astronomical way of expressing how fast something is moving when it is far enough from the Sun that the Sun's gravity has essentially no effect on it. The second interstellar object, given the formal designation 2I and the name of its discoverer, Gennadiy Borisov. But here is the thing that made Gennadiy Borisov almost the opposite of a relief, even as it confirmed that Oumuamua was not some unrepeatable accident of the universe. Gennadiy Borisov looked, in most of the ways that mattered most, entirely ordinary. It had a coma, a real, visible, normal coma, expanding around its nucleus the way a comet's coma should. It had a dust tail. It had water. It had CN, cyanogen radical, which is the chemical signature that has been detected in comets since the 19th century, and which is as familiar to comet spectroscopists as the smell of the sea is to someone who has lived near the ocean all their life. The chemistry was, in its broad strokes, the chemistry of a solar system comet. The nucleus was small, estimated at somewhere under 0.5 kilometre in radius, perhaps 1/5 to 2/5 of a kilometre, a modest worldlet of ice and rock that would fit comfortably within the distance a person could walk in under an hour. Its perihelion, its closest approach to the Sun, came on the 8th of December 2019 at a distance of roughly 2 astronomical units, roughly twice the Earth-Sun distance, safely outside the inner solar system, out in the cold where the asteroid belt gives way to the realm of the outer planets. Oumuamua had been bizarre. Gennadiy Borisov was superficially, reassuringly normal, and that normality was, in its own way, disquieting. Because if the first interstellar visitor had been a wild anomaly, something so strange it could almost be dismissed as a peculiarity specific to its unknown origin, then the second one, being entirely ordinary comet-like material, suggested that the population of interstellar objects was diverse, that there was not one type of interstellar visitor, but many, that the category contained multitudes, which meant that the strange one was strange for reasons having to do with its particular history, its particular composition, its particular origin, and not because interstellar objects as a class were all like that. Oumuamua's strangeness was its own, not shared. Borisov's ordinariness was its own, equally informative and in many ways more unsettling in what it implied about the breadth of what was out there. But ordinary is not the same as identical. And when the spectra were analysed in detail, when the chemistry was broken down into its components and the ratios were measured and compared against the library of solar system comets, something emerged from Gennadiy Borisov that did not fit. Carbon monoxide. Carbon monoxide, CO, one carbon atom bonded to one oxygen atom, a molecule that exists in space in many contexts and that is found in some solar system comets, was present in Gennadiy Borisov at a level that nobody had quite expected. The measurements came from multiple teams working independently, a team including Martin Cordiner and his colleagues, and a team led by Gennadiy Bodewits, both publishing in Nature Astronomy in 2020, and their findings told the same story from different angles. The ratio of carbon monoxide to water in Ōtautahi Borisov was roughly 3 times higher than what is typically observed in solar system comets. In some of the measurements, the enrichment was even more pronounced. This matters because carbon monoxide freezes only at very low temperatures, far lower than water ice, far lower than the temperatures found in the regions of our solar system where most comets form. In the protoplanetary disk that surrounded the young Sun 4.5 billion years ago, water ice could persist in the zones beyond the frost line, which lies roughly in the asteroid belt region. But carbon monoxide ice requires something much colder, found only in the outermost, most distant, most frigid regions of a forming planetary system, far from the warmth of the young star. An object extraordinarily rich in carbon monoxide relative to water is an object that formed in a very cold place, either in the extremely distant outer zone of its home planetary system or around a cooler, dimmer star than the Sun, or perhaps both. The carbon monoxide that Ōtautahi-Borisov carried across interstellar space and then began releasing as it warmed in the sunlight of our system was a chemical memory, a fossil record of the conditions in which it had formed, preserved in the ice that was sublimating off its nucleus as it rounded the Sun. It was, in the most precise and literal sense, carrying the fingerprint of an alien nursery. Not metaphorically. Chemically, the birthplace had left its mark in the ratios of the molecules, and those molecules were still there, still intact, still releasing their encoded information after however many billions of years the object had drifted through the cold between the stars. Around the time of perihelion, in the weeks following December 2019 into early 2020, Ōtautahi Borisov partially fragmented. It broke apart, at least partially, something that happens to solar system comets as well, when the stresses of solar heating and outgassing overwhelm the structural integrity of a nucleus that may be loosely bound to begin with. The fragmentation was observed, recorded, and added to the growing data set. It was, in a way, a final gift, another data point about the internal structure and strength of a body formed around another star. Before it, too, climbed away from the Sun and moved back outward into the dark from which it had arrived. And so the second rule broke differently from the first, where Oumuamua had broken the expectation that an interstellar visitor would behave chemically like what we knew, by having no chemistry at all, no visible outgassing, no classifiable volatiles. Ōtautahi Borisov broke a subtler expectation, the assumption, never quite stated but always quietly present, that alien comets, if they existed and if they were found, would look chemically like ours. That the ice and rock mix that formed comets in our solar system's early history was a universal recipe, the only way to build such a body, the same across all the planetary systems in the galaxy. What Borisov said, in the language of its carbon monoxide ratios and its alien chemistry, was no. The universe builds comets the way the universe builds everything else, by the local conditions, by the temperature and pressure and chemical composition of the particular disk around the particular star at the particular moment of formation. Our comets are our comets. Another star's comets are built by another star's rules. And when those comets drift free and cross between the stars on the long, slow currents of gravitational ejection, they carry their origin chemistry with them, intact across the light years, waiting for whatever instrument happens to catch them on the way through. The first two visitors had each broken something different. The first, the cometary and asteroidal dichotomy. The second, the assumption of chemical universality. Two visitors, two broken rules, two silent exits back into the dark. And then the surveys kept running. The automated telescopes kept sweeping. The nights kept accumulating. The expected population, extrapolated from the first two detections, from the models of how densely packed with interstellar fragments the galaxy must be to produce two detections in such a short time, pointed toward more. Not necessarily immediately, not necessarily on any predictable schedule. But statistically, probabilistically, in the aggregate, more. What no one knew, in the years between Borisov's departure and the next discovery, was how different the third visitor would be. Not just different from the two before it. Different in a way that shifted the frame of the whole question. Different in a way that reached not just across the solar system, but across time. The third one came from somewhere old, older than anyone had quite reckoned for. But before we arrive there, we need to linger a while in the story of the second visitor, because the second visitor deserves its own patient attention. It deserves it in part because of what it looked like, and in part because of what it hid, and in part because of the person who first caught it in the dark, alone, at a small telescope, in a place not generally associated with the leading edge of planetary science. His name was Gennadiy Borisov. He was an amateur astronomer working in Crimea, and on the 30th of August 2019. He was doing what amateur astronomers who build their own telescopes tend to do in the small hours of the night, which is sweeping the sky methodically, carefully, looking at whatever the sky had to offer on that particular evening. The telescope he was using had a mirror 65 centimeters across, roughly the width of a kitchen table, and he had built it himself. Which is the kind of detail that sounds like a pleasant biographical footnote until you consider what he found with it. What he found with it was a second interstellar object. Not a suspected one, not a candidate under investigation. An object with an orbit so emphatically, so decisively unbound from our Sun that there was no reasonable argument to be made for any other origin. The eccentricity of its orbit, the number that describes how closed or open a path is, where exactly one is the precise boundary between a closed ellipse and an open hyperbola, was approximately 3.36. Recall that Oumuamua, which had itself seemed extraordinary, had come in with an eccentricity of around 1.20, just barely above the line that separates solar system orbits from interstellar ones. Borisov's comet, by comparison, didn't just cross that line. It didn't creep past it. It hurtled past it with an orbital shape so dramatically curved that the Sun barely bent its path at all. The Sun, whose gravity manages to corral everything from Mercury to the farthest reaches of the Oort cloud, caught this comet the way you might catch a river by holding out your hand as a current rushes by. It registered, slightly, and then the comet moved on. Its speed coming in from interstellar space, the velocity it carried before the Sun's gravity had any appreciable effect on it, was roughly 32 kilometers per second. That is a useful number to carry for a moment before setting it down. At 32 kilometers per second, you could travel from London to New York in the time it takes to say the phrase out loud. You could cross the distance between the Earth and the Moon in about 2.5 hours. It was moving with the kind of speed that makes interplanetary distances feel almost intimate. The kind of speed that, paradoxically, makes the vast emptiness of interstellar space even more astonishing when you consider that arriving at 32 kilometers per second still meant the object had spent enormous stretches of time crossing the void between stars. The perihelion, the closest point the comet would reach to the Sun, came on the 8th of December 2019 at a distance of approximately 2.0 astronomical units. An astronomical unit is the distance from the Earth to the Sun, roughly 150 million kilometers, and 2.0 of them placed the perihelion of Borisov's comet just inside the orbit of Mars, on the outer edge of what we would ordinarily think of as the warmer regions of the inner solar system. For context, Oumuamua had come screaming into zero, 255 astronomical units inside the orbit of Mercury, close enough that the Sun's heat would have been ferocious against whatever surface it had. Borisov was gentler in its approach, cooler, more distant. It saw the Sun as a bright star rather than a furnace, and this, as it turned out, was part of what made its chemistry so interesting. Because the comet arrived, having spent its entire existence in very different thermal conditions, and those conditions had left their mark. But we are getting ahead of the chemistry. Before the chemistry, there is the comet itself, and the comet itself was the first surprise, because Borisov looked like a comet. This sounds obvious. It sounds like the least surprising thing you could say about a comet. But after Oumuamua, after months of debate about what exactly Oumuamua was, after the accumulated literature of hypotheses trying to account for an object that tumbled and accelerated and produced no visible coma, no tail, no gas, no dust, nothing cometary at all, despite apparently being pushed in a cometary way. After all of that, the community of planetary scientists watching the sky had arrived at a state of genuine uncertainty about what an interstellar object was supposed to look like. Oumuamua had been the only one, the only data point, and it had looked like a bare rock with a strange engine inside it that nobody could identify. So when Borisov appeared, with a genuine, visible coma already developing around it, and a real dust tail streaming away behind it, in exactly the way that comets in our own solar system behave when they approach the Sun, there was something almost disorienting about it. It looked like the thing it was supposed to look like. It looked like a comet, a real coma, which is to say a cloud of gas and dust sublimating off the surface as the Sun's radiation warmed it. A real tail, which is to say a trail of material blown back by the solar wind. Real water, real molecules, the kind of chemistry you can read in a spectrograph and recognize immediately as ordinary cometary material. It was, in most of its obvious observable characteristics, a perfectly normal comet, and this terrified the theorists, not literally terrified, but unsettled them in a deep way, because a perfectly ordinary-looking comet from another star meant something profound about the nature of comets in general. If Oumuamua had been the only detection, and it had been bizarre, one could construct a narrative, cautiously, tentatively, in which interstellar objects were simply strange, in which the process of ejection from another star system and the long transit across interstellar space did something to an object, altered it in ways that made it alien not just in origin, but in character. One data point is seductive that way. A single unusual thing can make you believe that unusual things are the rule. Borisov made 2 data points, and 2 data points that differ as dramatically as Oumuamua and Borisov differ do not tell you what interstellar objects are like. They tell you that interstellar objects vary, that the first one was not the template, that there is no template, that whatever processes produce comets and rocky bodies and icy fragments in the vicinity of other stars, those processes produce things that span at least as wide a range as the things our own solar system produces, and perhaps wider. This was, in a quiet way, one of the most important implications of the second detection. Not the object itself, but what the diversity of two detections implied about the population. Still, Borisov's ordinariness was the first layer. What made it genuinely strange was the second layer, and the second layer only became visible when the spectrographs resolved what the comet was actually outgassing, what molecules were being cooked off its surface as it fell toward the sun, what chemical story its evaporating body was telling to anyone who knew how to read it. The molecule in question was carbon monoxide. Carbon monoxide is a simple molecule, a carbon atom bonded to an oxygen atom, and it is not unusual to find it in comets. Our solar system's comets carry various mixtures of volatile molecules. Water ice is the dominant one, but there is also carbon dioxide, carbon monoxide, methanol, ammonia, and other compounds in different proportions depending on where in the solar system a given comet formed. Carbon monoxide is particularly interesting because it freezes at a very low temperature, much lower than water. At around -205 degrees Celsius, carbon monoxide transitions from gas to solid, which is cold even by the standards of the outer solar system. This means that a comet which contains significant carbon monoxide in its ice, rather than just on its surface, formed in an environment cold enough to trap it, to lock it in, to preserve it across billions of years of drifting in the dark. When researchers analyzed Borisov's outgassing spectrum, the work led by Martin Cordiner and colleagues, and separately by Gennadiy Borisov and colleagues, with results published in Nature Astronomy in 2020. What they found was that the carbon monoxide relative to water was roughly 3 times richer than you would typically find in a solar system comet. Not twice, not slightly elevated, 3 times. A substantial, unmistakable enrichment. This is the chemical fingerprint. This is what carries across the light years intact, sealed in ice since the moment the comet formed, preserved through the long emptiness of interstellar transit, and only released when the sun's heat finally reached it deeply enough to evaporate not just the surface layers, but the internal volatile stores. The excess carbon monoxide in Borisov's outgassing profile told a story about the temperature of its birthplace. The comet had formed somewhere exceptionally cold, or at least had formed in an outer region of whatever star system gave it birth that was cold enough to trap carbon monoxide at formation and keep it trapped ever since. This could mean a few things. It could mean the comet formed in the very distant outer zone of its home system, analogous to the region of our solar system beyond the orbit of Neptune, where temperatures are low enough that carbon monoxide-rich ices can condense. It could mean it formed in the disk around a cool star, a red dwarf or similar, where lower stellar luminosity would push the boundary for carbon monoxide ice formation closer in. It could mean its home system's outer disk was simply colder than ours, for some other compositional or structural reason. The spectra did not specify the mechanism, but they specified the condition, the cold, with enough precision to distinguish Borisov's birthplace from everything our own solar system has produced. It was a comet from another star, and it was built at temperatures our comets were not. Its chemistry was different not randomly, not in a way that destroyed the category of comet, but in a way that quietly rewrote what that category could include. An alien comet need not look like our comets on the inside, even if it looks like them on the outside. The surface appearance, the coma, the tail, the familiar ballet of sublimating ice, is a function of what the sun does to any icy body it heats. The interior chemistry is a function of origin. And origin was alien. There is a useful comparison here. Imagine picking up two smooth river stones from two different rivers on two different continents. To look at them, they are both smooth river stones. Same shape, same general texture, same process of formation by flowing water. But if you crushed them and analyzed their mineral content, you would find different minerals, different trace elements, different isotope ratios, the geological signature of the specific rock the river was eroding, which is the signature of the specific continent, which is the signature of a billion-year history of tectonics and uplift and erosion utterly distinct from anything the other river was carving through. The stones look the same. They are not the same, and the difference between them is a record of where they came from. Borisov was like that. A comet by appearances, an alien by chemistry. The outer story was familiar. The inner story was a document from another solar system, written in the language of molecular ratios and frozen volatile abundances, readable to anyone with a spectrograph sensitive enough to decode it. The nucleus itself was small. Estimates placed the radius of the solid body at somewhere under 0.5 kilometre. Some analyses suggested it might be as small as 200 to 400 metres across. This is a tiny body by the scale of the things we are talking about. Smaller than many asteroids that cross the inner solar system. Small enough that its own gravity is essentially negligible, that the material holding it together is less gravitational pull than the structural cohesion of whatever ice and dust and rock it is made of. The way a snowball holds together, not because the mass is sufficient to attract itself, but because it is simply stuck. A very small, very old, very alien piece of ice and rock from somewhere cold around some other star, drifting for an unknown length of time across an unknown expanse of interstellar space, and discovered on the 30th of August 2019 by a man with a telescope he had assembled himself in a region of the world that was not by any usual measure a centre of international astronomical research. This detail deserves its own moment. Gennadiy Borisov was not working with the resources of the Pan-STARRS 1 telescope on Haleakalā, which had caught Oumuamua with its array of advanced sensors and professional infrastructure. He was working with something he had built, which means he understood it intimately in the way that builders understand their tools. Every quirk and limitation and sweet spot calibrated through the process of construction itself. The 65-centimetre mirror he had ground and polished and mounted was not a small instrument. Amateur astronomy has progressed enormously in the past few decades, and a well-constructed 65-centimetre mirror can gather an impressive amount of light. But it was a personal instrument, a one-person operation, a single set of eyes at a single point on the planet on a single August night. And those eyes caught something that the entire apparatus of professional planetary science had not yet found. There is something worth holding there for a moment, in the stillness of a late summer night in Crimea, the kind of night where the Milky Way rises and the darkness is genuine, and the only sound is whatever a person's own thoughts make in the silence. A man looks through an eyepiece he ground himself, tracks across the sky in the systematic way that patient observers learn to do. And the cursor of his attention falls on a smudge of light that does not belong to any catalogue, that moves in a way that a solar system body does not, that turns out to be something that has travelled further than any human-made object has ever travelled, that has come from around another star and crossed the void between solar systems and entered our cosmic neighbourhood and been travelling through it for months before that particular telescope on that particular night caught it in its field of view. The universe, on that occasion, was found not by a large institution, but by a single person doing the thing they loved to do, in the dark, at an instrument they had built with their own hands. After discovery, the observations multiplied rapidly. Professional telescopes turned their attention to the new object. The full apparatus of modern planetary science, spectrographs and photometers and astrometric cameras on telescopes all over the world, began accumulating data on Borisov's comet in the months that remained before it passed perihelion and began its retreat. The chemistry was decoded, the orbit was refined to extraordinary precision. The coma evolved as the comet fell closer to the Sun, brightening gradually and then holding its brightness through perihelion. Perihelion came on the 8th of December 2019, and in the weeks around that date, Borisov was, in a strange way, almost too normal. It brightened approximately as expected. It outgassed approximately as a comet at that distance from the Sun should outgass. The tail developed, the coma expanded. Nothing that any experienced comet observer would have found surprising if they hadn't known the object's origin. And that very ordinariness felt uncanny in its own way, the sense that the universe had sent something from an incomprehensible distance, and it had simply done what it was supposed to do, followed the physics faithfully, responded to the sun's radiation in exactly the manner that ice and dust respond when warmed, as though the laws of thermodynamics were indifferent to how far from home a comet was, which of course they are. The laws are the laws. They apply across the light years with perfect consistency. Then, in March of 2020, something changed. Around and after perihelion, Borisov began to fragment. This is not unusual for comets in our solar system. The stresses of a close approach to the Sun, the differential heating of different parts of the nucleus, the outgassing pressures building up inside sometimes cause a cometary nucleus to crack, to shed pieces of itself, to come slightly apart. Several solar system comets have been observed to fragment in exactly this way, some dramatically, some subtly. The fragmentation of Borisov was observed in images taken in March 2020. Pieces of the nucleus showing up as distinct points or as an elongated structure in long exposure photographs, the comet beginning to disintegrate as it began its long outbound journey. Whether this fragmentation is unusual for an interstellar comet, whether it tells us something specific about the structural integrity of bodies that form around other stars, or about bodies that spend long periods in the cold between solar systems, we simply don't know. One data point, again, one fragmentation event in one interstellar comet, which could be typical or atypical, could be a consequence of alien origin, or could be the same kind of structural failure that solar system comets experience for entirely ordinary reasons. The knowledge is too thin to say. What it did offer was a last observation, a final signature before the comet passed out of range of useful study, receding toward the outer solar system and eventually into interstellar space on the far side. The fragments were the last clearly detectable traces of a body that had been travelling since some moment in its home system's history, perhaps billions of years ago, had taken some gravitational nudge that sent it out past its own star's outer boundary and into the long dark, and had finally arrived here, briefly warm, briefly visible, briefly studied, and then gone. Gone, in this context, means something specific. No orbit that begins with an eccentricity of 336 ends with capture by our Sun. Borisov's comet, like Oumuamua before it, was a visitor in the strict sense. It arrived with more energy than our Sun could contain. It swung around on a hyperbolic path. It borrowed the Sun's gravity long enough to curve its trajectory, and it departed on a new vector into interstellar space, altered slightly by the encounter, but fundamentally unbound, heading toward whatever happens to lie in the direction its new trajectory points, which is to say, heading into the dark on the far side of our solar system, never to return. We will not see it again. There is no future observation to schedule, no return apparition to anticipate, no cometary calendar entry to make. The object that Gennadiy Borisov found on a late summer night in 2019 made one pass and will not make another. Whatever happens to it over the next billion years, whether it gradually sublimes away in the interstellar cold, whether the fragmentation continues and it disperses into a diffuse cloud of particles, whether some future stellar encounter alters its trajectory again, will happen beyond any practical reach of human observation. The carbon monoxide enrichment remains the thing. Even after the last telescope lost useful signal, even after the fragmentation completed and the comet dispersed. The chemistry is what endures as the scientific contribution. The finding that an interstellar comet could carry a CO to water ratio 3 times richer than typical solar system comets means that the chemistry of comets is not fixed by the category. It is fixed by the birthplace. The birthplace is alien. The chemistry is therefore alien, and the alien chemistry is readable in the spectra, preserved across the transit, available to anyone with the instruments to detect it. This matters for what comes next. Because if the chemistry of one interstellar comet told us something specific about where it formed, about the temperature of the disk around whatever star gave it birth, then the chemistry of future interstellar comets will tell us similar things, each one a different story from a different nursery around a different star, each one carrying a record of conditions we could never observe directly, conditions around stars that may be hundreds or thousands of light years away, conditions that existed millions or billions of years before those comets arrived here. The interstellar comets are, in this sense, messengers, not in any metaphorical sense involving intention or design, but in the strict physical sense that they carry information encoded in their composition, information that survives the journey and can be decoded on arrival. Every future interstellar comet that passes through our solar system and gets a good spectroscopic observation becomes a data point about the diversity of chemistry in planetary disks across the galaxy, a sample from a lab we can never visit, delivered to our doorstep by the mechanics of gravitational ejection. Borisov demonstrated that this is possible. It demonstrated that the transit preserves the chemistry well enough to read it. It demonstrated that the spectrographs are sensitive enough to pick up the signal. And it demonstrated that the chemistry will differ, that we will not always be reading the same story, that each visitor is likely to carry a different record from a different place. 2 visitors, then, each breaking something different. Oumuamua broke the idea that an object was either a comet or a rock. It behaved like one while looking like the other, and the tension between those 2 observations has never been fully resolved. Borisov broke the idea that alien comets would look like our comets on the inside. It proved that the outer behavior could be familiar while the inner chemistry carried the unmistakable signature of a colder alien origin. 2 rules, 2 silences on departure, 2 arcs of carbon and ice and whatever they were made of, curving out of the solar system on trajectories they will follow until they reach whatever they reach next. And now, for reasons that have nothing to do with anything the comets themselves did or chose or were, and everything to do with what humanity built in the years between one detection and the next, there is a third. The third one is different from both of them. Different in ways that are not merely a matter of degree, but of kind. Oumuamua was a mystery about physics. What is it? Why does it accelerate? What is it made of that allows it to behave this way? Borisov was a mystery about chemistry. What does an alien comet carry inside it? What can we read from its composition? What nursery did it come from? The third visitor is something else. The third visitor is a mystery about time. It arrived from a direction that carried implications about age. Its speed, the velocity it carried in from interstellar space before the sun had any chance to accelerate it inward, spoke of a kinematic history unlike anything either of the first two had suggested, a history that placed its origin not in the young, thin disk of the Milky Way where our sun lives, but in the thick disk, the older, kinematically hotter stellar population that underlies and surrounds the younger neighborhood, the population of stars that formed when the Milky Way itself was still early in its history. The thick disk is a structural component of our galaxy that most people have never heard of, and it does not have a simple face-value name that conveys what it is. The Milky Way has a thin disk, which is the flat plane of the galaxy, where most of the young and middle-aged stars live, where the sun is, where the spiral arms are traced by bright blue clusters and glowing nebulae. The thick disk is older and broader and kinematically hotter, meaning that its stars move faster and in more inclined, more varied orbits than the thin disk stars. Because they formed in an earlier era when the galaxy's structure was less settled, and because billions of years of gravitational interactions have gradually scattered their orbits away from the flat plane. The stars of the thick disk are typically older than the Sun by several billion years. Some of them are among the oldest stars in the galaxy. If the third visitor came from the thick disk, and the models, careful as their uncertainties require them to be, point in that direction, then it is a relic from that early era. A piece of material that formed when the galaxy was young, around a star that itself formed when the galaxy was young, a star that has since had billions of years to evolve, possibly to expand and shed mass in its old age, possibly to scatter its outer system debris on the gravitational currents that eventually carry things free of their birth system and into the interstellar medium. An age model developed at Oxford by Matthew Hopkins and colleagues using what is called the Ōtautahi-Oxford population model, a computational framework designed to trace the kinematic histories of objects like this back through the dynamics of stellar populations, suggested that the third visitor could be over 7 billion years old. The Sun is approximately 4.6 billion years old, more than 7 billion years. Older than the star you are orbiting right now, by a margin of more than 2 billion years, a piece of ice and rock and chemistry that was already ancient when our solar system was still condensing out of its parent cloud of gas and dust. A fragment of some other planetary system's construction, launched long ago on a trajectory that eventually, after those billions of years of drifting between the stars, arrived here, in the inner solar system, moving at a speed no solar system body carries, outgassing in the sun's warmth as though waking up from a sleep of geological depth. That age estimate is a model-dependent number. This is important to hold clearly. The age was not measured directly. You cannot carbon date an interstellar comet, cannot read its age off its spectrum the way you can read its composition. The age comes from reasoning backward through the kinematics. Here is the speed and direction of arrival. Here is what those numbers imply about the stellar population of origin. Here is what we know about the ages of the stars in that population. Here is the resulting estimate. It is inference from motion, from dynamics, from the statistical properties of stellar populations in the Milky Way. It is rigorous inference based on real data and real models, but it carries the uncertainties that all such inference carries. 7 billion years is the estimate. The reality could be somewhat different. And yet, even allowing for the uncertainty, even holding the number loosely as the best current estimate rather than a settled measurement, the implication is extraordinary. The third interstellar visitor may be the oldest comet ever observed. Older than anything in our own Oort cloud, older than the Sun itself, a traveller from the Milky Way's early history who has been crossing the dark for longer than our planet has existed. It arrived from the direction of Sagittarius, from the general direction of the galactic centre, which is consistent with the thick disk origin, with the kinematic signature of a stellar population whose orbits bring them through and around the central regions of the galaxy in patterns different from the nearly circular orbit of our own Sun. It came in fast, faster than either of its predecessors, faster at approximately 58 kilometers per second before any solar system effects than any interstellar object yet observed. Where Oumuamua arrived at around 26 kilometers per second and Borisov at around 32, the third visitor arrived at nearly double that, crossing the threshold of our solar system with a speed that reflects the kinematic energy accumulated over billions of years of gravitational interactions with stars and molecular clouds and the mass distribution of the galaxy itself. The orbit it traced has an eccentricity of approximately 6.1. The eccentricity of Oumuamua was 1.20, of Borisov 3036. The crescendo across the three objects, 120, 336, 61, is a built-in escalation in the data, an arithmetic progression of increasing strangeness, each visitor more emphatically unbound than the last, each one wearing its interstellar origin more obviously, each one arriving with a trajectory more dramatically divorced from anything the solar system could have produced on its own. A body with an eccentricity of 6.1 has so much more energy than the escape velocity from the Sun that it barely registers the Sun's gravity as a significant perturbation. It came through our solar system the way a comet crosses an empty field. The Sun held it, briefly, in the loose sense that the Sun's gravity forced a slight curve in its path. But the path was never in question. The name it received in the catalogues is 3I/Atlas, also catalogued as Comet C 2025 N1. The Atlas in the name is not a person but a system, the Asteroid Terrestrial Impact Last Alert System, an automated survey network built originally to identify near-Earth objects on potential collision courses, running all sky sweeps repeatedly and quickly enough to provide warning time before any such impact. It was the Atlas telescope at Río Hurtado in Chile that first recorded the light of this ancient traveller on the 1st of July 2025. It was already showing signs of cometary activity at discovery. A developing coma, the first signatures of outgassing beginning as the comet descended toward the Sun, warming gradually, the surface beginning to sublimate, the volatile ices, locked in for billions of years in the dark, beginning to respond to the radiation of a star they had never encountered before in any of their previous history. And so we come at last to the third visitor. The oldest, the fastest, the most extreme in its orbit. Still weeks from its perihelion when it was discovered, but already alive, already breathing in the language of evaporating ice, already leaving its chemistry open to any telescope that could read it. The third visitor broke the last assumption the first two had left standing. It broke the assumption about when these objects come from, about how old they might be, about how deep into the galaxy's history their origins might reach. It came from the thick disk. It came from the early Milky Way. It came from a time before the sun existed, from a world we will never know, around a star we cannot identify, carrying chemistry that formed under conditions billions of years gone. 3 visitors. 3 different rules undone. And the telescopes were still running, and the sky was still dark, and there were more of these things in the dark than anyone had reckoned on. The third visitor, catalogued formally as Comet C 2025 N1, was given the designation 3I Atlas, the third interstellar object in the record, and the first discovered from the southern hemisphere by a telescope array whose original purpose was the early detection of asteroids that might one day threaten the Earth. There is something quietly significant in that arrangement. The instruments built to watch for danger found instead a relic. They found a comet from before the sun, and what it threatened was not any city or coastline, but a particular idea. The idea that the space between the stars is mostly nothing, mostly dark and largely empty of anything worth study. A vast and featureless void between the real things, the luminous things. The stars and planets and the living worlds we imagine might exist among them. That idea did not survive the summer of 2025. The orbit, when the calculations came back, was the most extreme of the 3 by a wide margin. The eccentricity of Oumuamua had been approximately 120, and that number had been enough to announce its interstellar origin beyond any reasonable doubt, because a value of 1. 0 is the knife edge between a path that curves back and a path that does not, and Oumuamua was well above it. Borisov, the second visitor, had arrived with an eccentricity of approximately 3.36, which was so far above the threshold that even a very large uncertainty in the measurements could not have pulled it back across the line. And now 3I Atlas came in at approximately 6.1. Each number had been larger than the one before it, a progression that reads less like coincidence and more like the 3 objects were competing to demonstrate something. To make the point emphatically, each time more emphatically, that the interstellar medium is not a rare sender of visitors, but a generous one, and that its gifts arrive with speeds and trajectories entirely unrelated to the gentle, near-circular architecture of the solar system they are passing through. The speed confirmed the same pattern. Oumuamua had been travelling at approximately 26 kilometers per second relative to the Sun at a great distance from it, a velocity that in ordinary human terms is almost unimaginable, a distance roughly equal to the span of a continent, crossed in a single second, yet it was. In the context of interstellar objects, unremarkable, Borisov had arrived at approximately 32 kilometers per second, and 3I Atlas came in at roughly 58 kilometers per second. More than double Oumuamua's speed. More than 1.5 times Borisov's. Faster than any natural visitor from outside the solar system that any telescope had ever recorded. On the list of the fastest things humanity has ever built and sent away from Earth, 58 kilometers per second would be extraordinary. For a comet arriving from a distant reach of the galaxy, it was, in a sense, ordinary. It was what you get when an object has had billions of years to accelerate through the differential gravitational field of the Milky Way. When it comes from a stellar population whose stars have been orbiting the galactic center since an epoch that predates our own sun's birth by a margin that the mind struggles honestly to hold. It came from the direction of Sagittarius. From the direction of the galactic center, the crowded, ancient, blazing heart of the Milky Way. Not that it originated there, the trajectory, traced back through time, pointed toward that region of the sky, and what astronomers read from that pointing was not a galactic center origin, but a kinematic affiliation with the thick disk, the old stellar population that wraps around the plane of the Milky Way in a layer thicker and older and more kinematically disordered than the thin disk where the Sun lives, where the younger stars congregate, where most of the stars you might see on a clear night were born in the last few billion years. The thick disk is different. It is where the Milky Way's older generations live, stars that formed when the galaxy was still settling into its present shape, stars whose motions carry the memory of a younger, more turbulent galactic history. Objects that move with the thick disk tend to move fast relative to the Sun, because the Sun and its neighborhood are part of a different, calmer kinematic stream, and objects from outside that stream carry a velocity surplus that reflects the difference. The question of how anyone could know where 3I Atlas came from, how anyone could assign it an age that stretches back beyond the formation of our own solar system, is a fair one to ask. And the answer lies not in any single measurement, but in the kinematics, in the mathematics of orbital tracing, of working backward through the motions of a fast-moving object to ask what population it could plausibly belong to, what region of the galaxy, what epoch of stellar history. Matthew Hopkins and colleagues at Oxford applied the Ōtautahi-Oxford population model to the problem. A model built to describe the kinematic distributions of objects in different galactic populations, to trace where fast-moving interstellar visitors are most likely to have originated, and what that model returned as a best current estimate, and it is worth resting on that phrase, because this is model-dependent work, the kind of careful scientific inference that is more confident than a guess, but less certain than a direct measurement, was that 3I/Atlas was likely a member of the thick disk population, and that it was plausibly more than 7 billion years old. 7 billion years. The Sun is approximately 4.6 billion years old. The Earth is slightly younger than that. Whatever world this object came from, that world, if it ever resembled a world in the way we understand the word, existed before our Sun had ignited. The protostellar cloud that would eventually collapse into the Sun and its family of planets had not yet begun to contract when. Somewhere in the thick disk of the young Milky Way, a solar system formed around a star we will never identify, and that system went through the full cycle of planet formation, and in the process of that formation, icy debris was flung outward by the gravity of forming giants, and eventually by the slow mechanics of stellar passage and gravitational stripping. Some of that debris was set loose entirely, given enough velocity to leave its home system behind and wander the galaxy as a free traveller. And one of those travellers, after a journey measured not in years or centuries but in billions of years, fell at last into the gravitational influence of our Sun, warmed for the first time by a star that had not yet existed when it was cast adrift, and began to outgas, began to show the coma that the Atlas telescope in Chile would detect on the first day of July 2025. The spectral measurements arrived from multiple instruments in the weeks and months that followed, including observations from the James Webb Space Telescope, which turned its extraordinary sensitivity toward this ancient visitor and read the chemical story encoded in its light. What it found was a comet with a striking abundance of carbon dioxide relative to water. CO2, carbon dioxide, is a volatile compound. It requires cold to remain frozen, and it sublimates, it turns from ice directly to gas, at temperatures reached at greater distances from the Sun than water ice does. A comet rich in carbon dioxide is telling you something about the cold from which it came, about the temperature of the distant outer zone of whatever system formed it, about the conditions present in a solar nebula that existed billions of years before our own. The spectra also showed water ice and dust, confirming the cometary nature of the object, and early observations noted nickel emission with relatively little iron, an unusual chemical signature that had also been noted in a different form in the analysis of Borisov, and that carries its own information about the conditions of the object's formation, though the interpretation of that signature is still a matter of active investigation among the researchers who study it. The Hubble Space Telescope did something different. It tried to see through the coma to the nucleus beneath, the developing cloud of gas and dust that surrounded 3I/Atlas as it fell toward the Sun made direct measurement of the solid body very difficult. The coma inflates the apparent size of the object in any image, spreading the light outward from the nucleus in a way that makes it nearly impossible to say with confidence where the comet ends and the surrounding cloud begins. But Hubble constrained the nucleus to smaller than a few kilometers, roughly under approximately 5 kilometers on its longest dimension, and quite possibly much smaller than that. In the context of this trilogy of objects, 3I/Atlas was likely the largest of the three nonetheless, though the uncertainty in that comparison is real and should be held lightly. Oumuamua had been estimated at perhaps 100 to 400 meters on its long axis. Borisov's nucleus had been estimated at under about half a kilometer in radius. 3I/Atlas, even at the lower end of the Hubble constraint, was probably bigger than either of them. But bigger, in this case, is a relative word. These are not large objects by any ordinary reckoning. They are fragments, shards, the kind of debris that forms by the billions around every planetary system that has ever existed. Its perihelion, its closest approach to the Sun, came in late October of 2025 at a distance of approximately 1.36 astronomical units, just inside the orbit of Mars. It passed on the far side of the Sun from Earth, out of convenient reach of many ground-based telescopes during that critical period, and it never came close enough to the Earth to pose any concern, with its nearest approach to our planet estimated at approximately 1.8 astronomical units in December of 2025. And then it was leaving. As Oumuamua had left, as Borisov had left, each of them departing along a trajectory that leads nowhere in the solar system, because the solar system's gravity is simply not strong enough to hold something moving this fast, something that was never gravitationally bound to this star in the first place, something that belongs to the open space between the stars and is merely passing through. We will not see 3I/Atlas again. We will not see any of the three again. This is one of the truths about interstellar objects that requires a moment to sit with in the quiet of a room at the end of the day, because it is a different kind of loss than the ordinary disappearance of a thing behind a hill or around a corner. Oumuamua crossed our skies in 2017 and was outbound before most people had heard of it. And it is now somewhere in the outer solar system on its way out, and in a few thousand years it will pass the heliopause and re-enter the true interstellar medium, and it will drift onward into a future no human civilization may live to observe. Borisov did the same, and 3I/Atlas, moving even faster, will exit the solar system even more quickly. They came, all three of them, in a window brief enough that the astronomers who observed them can still sit at their desks and remember where they were when the discovery papers arrived. And then they were gone, and the sky was the same dark sky it had always been, and there was no way to follow them. No spacecraft that could be launched on a trajectory fast enough to intercept any of them before they crossed the boundary between the Sun's domain and the open galaxy. But consider what three departures teach. Read together. Consider the crescendo they represent. The eccentricities are 1.20 and 3.36, and approximately 6.1. Each one larger than the last, each one farther above the 1.0 line that separates bound from unbound, each one telling you more emphatically that the solar system is embedded in something it cannot hold. The speeds are 26 and 32 and 58 kilometers per second, each one faster than the last. Each one carrying more information about a broader, more kinematically diverse origin population, the interstellar medium not as a single homogeneous source, but as the accumulated output of every stellar generation the Milky Way has ever produced. The young thin disk stars and the old thick disk stars, and everything in between. All of them gradually leaking debris into the space between them over billions of years, the galaxy slowly filling with the cast-off material of countless solar system formations. The objects are Oumuamua, bare and tumbling and mysteriously accelerating, and Borisov, ordinary-looking and yet chemically foreign, and 3I/Atlas. Ancient and fast and steaming with CO2, and still active as it rounds a star that is younger than itself by billions of years. Three different rules. Three different assumptions that could not survive contact with the evidence. The first assumption Oumuamua undid was the clean boundary between comet and asteroid, the idea that a small body in space is one or the other, that its behavior and its appearance belong to the same category, that something that looks like bare rock behaves like bare rock. Oumuamua looked like a bare rock, and it accelerated without any visible tail to push it, and the rock or comet dichotomy simply bent under the weight of that contradiction. Something was happening inside it or on its surface that the instruments of 2017 could not detect. And the range of explanations that serious astronomers proposed, faint clean outgassing invisible to the telescopes of that era, a nitrogen ice shard chipped from the frozen surface of a Pluto-like exoplanet, a hydrogen iceberg, a fractal aggregate of dust so loosely bound that sunlight itself could move it, says more about the limits of human instrument capability in 2017 than about any weakness in the science. The mystery is real. The non-gravitational acceleration, measured by Micheli and colleagues in 2018, is a real measurement, published in Nature, reproducible in the data. What pushed it remains, as of the time of this narration, genuinely unresolved. And there is a kind of intellectual honesty required to hold that, to say that the first interstellar object ever studied left us with a question we cannot yet answer, and that this is not a failure, but a condition of standing at the edge of something new. The second assumption Borisov undid was more subtle, but in some ways more important. Because after Oumuamua, after the tumbling, elongated, mysterious, accelerating rock, there was a temptation to think that interstellar objects are strange by nature, that the strangeness of Oumuamua was typical, that anything arriving from outside the solar system would be as exotic as Oumuamua had been. And then Borisov arrived and looked almost exactly like a solar system comet, coma, tail, water, the normal molecular inventory that any observer of ordinary comets would recognize, and for a moment it seemed that perhaps Oumuamua was the anomaly, and interstellar objects in general are just comets. Comets like our comets, familiar, unremarkable, expected. But the carbon monoxide overload was there in Borisov's spectrum. approximately 3 times richer relative to water than in typical solar system comets, and CO freezes only in very cold environments, and the chemistry was carrying the memory of a birthplace far colder and farther from its original star than any comet in our solar system is thought to have formed. Borisov's chemistry was alien even when its appearance was not. The lesson was that the sample of interstellar objects is diverse, that we cannot expect them to follow a single template, that the galaxy produces different things under different conditions around different stars of different ages and compositions, and that the interstellar medium is not a single thing moving past us, but a mixture, a blend of the output of billions of distinct stellar systems, each with its own history and its own chemistry and its own debris field. And then the third assumption, the assumption about time itself, about how old these visitors might be, about whether they are roughly contemporaneous with the solar system or whether they might predate it. 3i/Atlas left that assumption without a foundation to stand on. Something older than the Sun had fallen into our solar system and rounded our star and departed again. And it had still been active, still outgassing, still responding to the light of a younger star with the sublimation of ices that had been sealed inside it since a time before the Earth existed. 7 billion years is an estimate, a model-dependent inference, the output of the Ōtautahi-Oxford model applied to the kinematics of a single fast-moving object. And the uncertainty in that number is significant, and the scientists who produced it would be the first to say so. But it is a best current estimate based on the best available tools, and even if the true age is somewhat less, even if 3i/Atlas is 5 billion years old rather than 7, it is still older than the Sun, and the claim is still extraordinary. Now consider what 3 detections in 8 years implies about the background population of these objects. This is where the arithmetic of the interstellar medium becomes the most quietly astonishing part of the story. When Oumuamua was detected, astronomers faced an immediate calculation. They had one detection. Pan-STARRS 1 sweeps the sky at a certain cadence and to a certain depth. And there is a well-understood relationship between how often a survey of that capability detects something and how many of that something must exist in the volume of space the survey is watching. Working through those numbers, the estimates that emerged from that calculation, the work of Doe, Tucker and Tonry in 2018, and related analyses, suggested something in the range of approximately 10 to the power of 15 interstellar objects per cubic parsec of space. A parsec is a unit of distance used in astronomy, approximately 3.26 light-years, a distance so vast that it takes light itself more than 3 years to cross it. And a cubic parsec is that distance cubed, a volume of space incomprehensible in ordinary terms. A region large enough to contain many star systems within it, and within each such cubic parsec, the estimate placed approximately 1 quadrillion interstellar objects. Expressed across the full volume of the galaxy, the implied total number of such fragments is something in the range of 10 to the power of 25 or 26 10 septillion, a number that is written as a 1 followed by 25 or 26 zeros. It is worth acknowledging directly that these numbers are extrapolations from very few detections, order of magnitude estimates built on incomplete survey data, and they carry large uncertainties. They are not precise measurements. But they are the best available guide to the scale of the phenomenon. And the scale, they suggest, is one that changes how you think about the space between the stars. Thousands of interstellar objects drifting through the volume of the outer solar system at any given moment. not as exceptional visitors, but as a permanent background population, a constant streaming of material from distant systems through our own, silent and invisible until an instrument sweeps the right patch of sky at the right sensitivity at the right moment. They have been here all along. They were here before the sun ignited. They were here while the planets formed. They were here when the first life appeared in the oceans of the early Earth. They were here when the first human beings looked up at the night sky and began to wonder what it contained. They have always been part of the solar system's environment in the same way that the cosmic ray background is always part of the environment, or that the slow, steady rain of micrometeorites is always part of the environment. We were simply not able to see them. The mechanism by which they are produced is the same mechanism that built the solar system. During the formation of planetary systems, the gas and dust disk surrounding a young star begins to coagulate into planetesimals, rocky and icy bodies that will either become planets or their moons, become asteroids or comets, or be gravitationally scattered by the growing giants before they can settle into stable orbits. When a giant planet forms, something the size of Jupiter or Saturn, with a gravitational influence enormous relative to the small icy bodies it shares its early orbit with, it can fling debris outward with tremendous force. Some of that debris is sent into very distant, loosely bound orbits, forming the Oort cloud analogue of the system in question. Some is sent away entirely, given escape velocity, sent out into interstellar space with no possibility of return. Every system that has ever formed giant planets has done this. And later, as those systems evolve, as stars age and move and pass close to one another over billions of years, the outer reaches of Oort cloud-like structures can be stripped by the gravitational tides of passing stars, releasing further material into the interstellar medium. Planet formation is, in a sense, a process that saturates the galaxy with its waste. The fragments that could not be incorporated, the icy shards that were flung or stripped or slowly diffused outward, they have been accumulating in the spaces between the stars for as long as planetary systems have existed, which is to say, for as long as stars have existed, which is to say, for a very long time. What changed between the era before 2017 and the era after is not the population of interstellar objects. They were always there, always moving through, always briefly illuminated by our sun as they passed. What changed is the instruments. Pan-STARRS 1 on Haleakalā. The mountain in Hawaii, whose name means the House of the Sun, began systematic survey operations in a mode capable of detecting fast-moving, faint, one-time visitors. Atlas, the asteroid terrestrial impact last alert system, with its telescopes in Hawaii and Chile and South Africa and elsewhere, extending the sky coverage and the cadence of observation. And now, gradually coming to full operations, the Vera C. Rubin Observatory in Chile, which carries the largest digital camera ever built for astronomy, a camera designed to image the entire visible sky every few nights to an extraordinary depth, sensitive to objects far fainter than any previous survey telescope has reached with the same frequency. The legacy survey of space and time, the decade-long all-sky survey the Rubin Observatory is conducting, is widely expected to convert interstellar object detection from an event, something that happened once in 2017, once in 2019, once in 2025, into a routine cadence, plausibly one or more per year. Dozens over the course of the survey's full decade. The 8-year window that contained all 3 confirmed visitors is not, in retrospect, a puzzle to be explained by some coincidence of arrival timing or some anomalous influx from a particular direction. It is simply the window in which human astronomy became capable of seeing what was always there. The 3 in 8 years are the first 3 data points of what will become a steady accumulation. The archive of interstellar objects will grow. Each new detection will add information, another set of spectra, another orbit, another composition, another origin population, another piece of the picture of what the galaxy's debris field looks like across different stellar ages and chemical environments. And astronomers will eventually be able to say, with the confidence that comes from a real sample rather than 3 remarkable anomalies, what interstellar objects are typically made of, and how they vary, and what the distribution of their ages and origins implies about the history of planetary formation in the Milky Way across cosmic time. That is where the 3 visitors lead. Not to certainty, not to answers already in hand, but to the threshold of a new kind of observational astronomy, one in which the solar system is understood not as an isolated enclosure, but as a porous one, permeable to the relics of other worlds, visited constantly and quietly by the material output of a galaxy that has been building and scattering and drifting for billions of years more than. The Sun has existed. 3 visitors, 3 broken rules, and behind them, in the direction from which they came and the direction in which they are going, the rest of the population, the tens of quadrillions of fragments that the models require, the ancient icy shards of solar systems we will never directly observe, the billion-year travellers whose host stars have long since dimmed or exploded or slowly faded into the class of stellar remnants. The debris field of the galaxy moving through and around us in the dark, patient and invisible and everywhere at once. The space between the stars is not empty. It never was. That is perhaps the simplest version of what these 3 objects say together, said as plainly as it can be said. The interstellar medium carries within it the material record of every planetary system the galaxy has ever produced. The void between the stars is not a void, but an archive, slow-moving, ancient, perpetually in transit, carrying chemical fingerprints of worlds that formed under conditions utterly unlike anything in our own solar system. Worlds colder or hotter or richer in carbon or poorer in water, around stars redder or bluer or more metal-rich or more metal-poor than the Sun, in environments that existed before the Earth's crust had finished cooling or before the first ocean had filled its basin. All of that history is encoded, imperfectly and partially, but genuinely, in the chemistry and kinematics of the objects drifting past us. And the telescopes are now sensitive enough, and numerous enough, and fast enough to begin reading it. There is a particular quality to what these 3 visitors leave behind when you consider them all together, a quality that is different from the ordinary aftermath of a scientific discovery. Most discoveries add a new fact to the inventory of things humanity knows. These 3 add something more structural than a fact. They change the frame inside which the night sky is understood. The sky you see on a clear night, if you are somewhere far from city lights and the air is still and the stars are bright, that sky contains within it not only the Sun's family of planets and asteroids and comets, but also a constant quiet traffic of visitors from elsewhere. Fragments of other histories crossing the solar system at speeds that the gravity of the Sun cannot slow enough to capture, moving through and away and onward toward whatever lies in the direction they are travelling, which is to say, nothing in particular, no destination, just the open galaxy stretching away in all directions with its 100 billion stars and its archive of displaced material and its slow, ongoing exchange of debris between systems too distant to interact in any other way. Oumuamua is somewhere out there now, past the orbit of Neptune in all likelihood, tumbling in whatever chaotic rotation it has maintained since the forces that shaped it first set it spinning, reddish and elongated, and carrying its unresolved question with it into the dark. Borisov is out there as well, slightly fragmented, carrying its overabundance of carbon monoxide, its chemical memory of a cold alien nursery somewhere among the stars. And 3i Atlas is leaving too, past its perihelion now, the warmth of the sun already fading as it climbs back out along its hyperbolic path at 58 kilometers per second. The sublimation of its ices slowing as the temperature drops, the coma gradually thinning. The ancient material that briefly steamed and glowed in the light of a younger star settling back toward quiescence for the long journey ahead. It will cross the orbit of Mars. It will cross the orbit of Jupiter. It will reach the outer solar system and continue, and the heliosphere will thin around it and then be left behind. And it will re-enter the interstellar medium it has travelled through for billions of years, and the sun will become just one more point of light among many, growing fainter behind it, and eventually indistinguishable from the stars. We found them here, in the brief interval when their paths intersected ours, when the solar system's light touched the ices and the dust and the ancient chemistry they carry, when the telescopes were watching and the nights were clear and the moment could be recorded. For Oumuamua, the window was only a few weeks before it was too faint to observe. For Borisov, somewhat longer, given the advance notice of its discovery and the brightness it achieved. For 3i Atlas, the instruments were ready, the survey was running, and the observations accumulated in the months before and after its perihelion with a richness that would have been impossible a decade earlier. And now the survey continues. The Vera C. Rubin Observatory is running. The legacy survey of space and time is accumulating data. Somewhere in the solar system tonight, or this month, or this year, there are interstellar objects passing through that no telescope has yet caught in its field of view, too faint, or in a part of the sky that has not been imaged at the required sensitivity on the required night. They will not all be caught. Many will pass and depart undetected, slipping out of the solar system with no record in any catalogue. But the probability of catching the ones bright enough or close enough or in the right part of the sky is growing. Each year the survey accumulates more data and the pipelines become more refined and the alerts go out faster. And the telescopes that respond to those alerts point faster and deeper than the ones that pointed at Oumuamua in 2017. The archive is being built. If you are somewhere that lets you see the sky tonight, if you are near a window, or if the thought of the sky is enough, if you can hold the image of it in your mind while the room around you grows quieter and the day begins to recede, consider what the dark beyond the stars contains. Not as metaphor, not as poetry, but as a physical fact that survey telescopes have begun to confirm, one detection at a time. The space between the stellar points of light is not absence, it is material, it is ancient, it is moving. It carries the chemical signatures of planetary nurseries that existed before the sun, and it streams past us continuously, most of it invisible, some small fraction of it eventually entering the solar system on hyperbolic trajectories that carry it briefly close enough to a telescope to be found and named and studied, and then lost again to the dark. 3 visitors, named and recorded. 3 broken rules, honestly reported. 1 revelation, quietly extraordinary. The emptiness between the stars is an illusion, and we are only now, with the instruments of this particular decade, beginning to see through it. Let the thought settle where it will. Let it become part of the background of the night. Another layer in the dark, the comet from before the sun, the rock that sped up without a tail, the ordinary-looking alien comet carrying its chemical secret. They are all out there. There are more behind them, behind the ones we could not see, behind the ones the survey will find next year and the year after. The galaxy is not keeping this quiet. It has been sending us these things for as long as the solar system has existed. We are only now learning to receive them. If you are still awake and you want to share where in the world you are listening from tonight, the comments are there, and I read them. There is something worth knowing in the idea that people on opposite sides of the earth are drifting towards sleep inside the same story about objects older than the sun. You have done enough for one evening. Put down whatever remains of the day. The survey telescopes are still running, the sky is still dark, and somewhere in the outer solar system, an ancient fragment from a world we will never know is climbing back out toward the stars it came from, carrying its cargo of frozen history away from us at 58 kilometers per second, unhurried by the scale of what it crosses, patient in the way that only something very old and very free can be. Good night from up here in orbit. I'll keep watch while you drift.